Welcome to Calculus. Today we will investigate evaluating integrals using the fundamental theorem of calculus 2. We'll take a look at 3 examples. Our instructions here define formulate for the functions that are represented by these integrals. So looking at example number 2 here, I have the integral from lower limit of integration 2 up to x of 12t squared minus 8t dt. Well, we want to apply the fundamental theorem of calculus 2 to evaluate this, so we should see what the fundamental theorem of calculus 2 says. So here's a version of it. If f of x is continuous on the open interval I with an element of I, so just to mark what pieces we're really referring to, the f of x is my 12t squared minus 8t. So that satisfies the hypothesis. That's a continuous function on an open interval. And the a is this 2. So definitely 2's in the domain of this function. So far we're good in terms of satisfying the hypothesis. The conclusion's there in red. Then the area function a of x equals the integration from a to x of f of t dt is an antiderivative of f of x on I. And we'll put that in 2 different ways. The first way is that the derivative of the area function is f of x, or spelled out more, d dx of the integration from a to x of f of t dt equals f of x. We have that final part of our conclusion that a of x also satisfies the initial condition a at lowercase a equals 0. So let's apply this fundamental theorem of calculus 2 to write a formula that would represent this integration. In other words, what would be my f of x? So we'll start off, we really just want to integrate as normal, and then we're going to treat this like definite integration, since I do have a lower limit and an upper limit, even if this upper limit's a variable. So I'm going to start off by saying that this integration is equal to, starting to integrate here, 12, and here's the antiderivative of t squared, so that's going to be 1/3 times t to the power of 3. Then I'll treat this second term, minus 8t, to find its integral, so minus 8, that's the constant coefficient. And then the antiderivative of the linear parent t is going to be half times t squared. So we take the integration as usual, and we want to run from 2 up to x. So at this point, I'm ready to substitute in my limits of integration and simplify. So 12 times 1/3 is going to be 4. And then I want to start substituting in. So I've got x as my upper limit of integration, so I'm substituting that for t. So that's 4x cubed. I see that 8 times 1/2 is also 4, so minus 4x substituted in for t squared. Now we'll do the same with the lower limit of integration. So this applies really the fundamental theorem of calculus 1. Here we're going to plug in the 2 for t. So this is going to be 4 times 2 cubed minus 4 times 2 squared. So we've integrated, and what's left for us to do to find this f of x is just to simplify this statement. So this is going to be equal to 4x cubed minus 4x squared. So that comes out of the parentheses. And I want to just find this number value. So this is 4 times 2 cubed. 2 cubed is 8, times 4 is 32. 4 times 2 squared is 4 times 4 is 16. So that difference is 16. And then we'll just pick up our sign. And that finalizes the integration. We've written a formula to represent that definite integration from 2 to x. Make sure I get my cube there. So that example's for really a polynomial, a quadratic f of x. Let's take a look at a trigonometric integrand. Here we have the integration from negative pi over 4 to x of secant squared theta d theta. So we'll jump right into the integration. I need to think about what would the antiderivative for secant squared of theta be. So if I've got secant squared of theta as my derivative, to think the antiderivative, what would have been the original function that yielded the derivative secant squared of x? Well, that's got to be tangent. In this case, I'll keep my variable there, theta. So that's how I'm going to integrate here. So a lot fewer terms with this function. So we'll take tangent of theta, and that we're going to integrate from negative pi over 4 to x. So just like with our previous example, we'll apply the fundamental theorem of calculus 1 to evaluate this. This is going to be tangent of x. X is substituting in for theta, minus the tangent of the lower limit of integration, negative pi over 4. So that first term is complete. We just need to evaluate tangent at negative pi over 4. So visualizing the unit circle, negative pi over 4 would be the 45. And so when we think about what the value of tangent would be at that angle, the x dimension is square root of 2 over 2 at 45. And since this is below the x-axis, the y dimension is going to be negative square root of 2 over 2. And then recall, tangent is the vertical divided by the horizontal. Since those are the same but just opposite in sign, this is going to have the value of negative 1. Again, just to visualize, tangent at negative pi over 4 would be negative square root of 2 over 2 over square root of 2 over 2. And that would reduce to negative 1. So for our final answer here, we're going to have that the integration using these limits from negative pi over 4 to x of secant squared theta d theta is going to be tangent of x plus 1. That double negative will cancel to become a positive. So that's an example of a trigonometric function. Let's take a look at one last example that involves the exponential base e function. So here we've got the integration from 3x to 9x plus 2 of e to the power of negative u du. So as I start here, just the same as my previous example, I need to think in terms of how I would have created that antiderivative. Well, how would I have gotten the e to the power of negative u if that was my derivative? Again, we'll think, what would the original function have been to get the derivative e to the negative u? Well, we know that it's going to be e to the negative u because e function always is its own derivative. And by extension, we can logically say it is its own integral. One thing I would need to note here is that according to the chain rule, if my original function was e to the power of negative u, the derivative would have the value of that times the derivative of the u function. So let's make sure that we note that difference. Let me rewrite here. So again, if the derivative is coming from e to the power of negative u, it's going to be that, but times the derivative of negative u, which is negative 1. So what I need to do to be able to integrate here is I need to place a negative on e to the negative u, but I know that its original sign was positive, so I'm going to place a second negative out front of the integration, and that'll ensure that it really would cancel. But I just need this form here so that I can get the correct antiderivative. So we're ready to go. This is going to be equivalent to negative, so I'm just pulling that negative out front first, times the antiderivative of this, which we found was e to the power of negative u. And we're integrating this from 3x, lower limit of integration, to upper limit 9x plus 2. So we're ready to substitute our limits of integration in. So negative e to the power of negative, our upper limit's 9x plus 2, minus e to the power of negative, lower limit 3x. We'll distribute our negatives. There's a few of them here. So this negative is going to distribute to both terms. And then in the power, this negative is going to distribute to both terms. So final answer for us is going to be negative e to the power of negative 9x minus 2. Second distribution of the negative is going to cancel with the negative that was there. So plus e to the power of negative 3x. And that completes that integration. Well, thank you for joining for this investigation of integrating using the fundamental theorem of calculus 2. See you soon.